Hello, this video is on general logarithmic functions. We're getting very close to the end of this section in James Stewart's Calculus 6th edition, chapter 7. He has this little, it's even in a different color, these pages, where he goes through exponential functions and natural logarithm functions and general logarithm functions. This video is on general logarithmic functions. Okay, this is a to the x, a to the power of x. It has an inverse function. A to the x is the exponential function, where a is a base and x is a variable that can change. So you see it's the opposite of the power function. The power function is a variable raised to a constant. The exponential function is a constant raised to a variable. Anyway, watch previous videos. So this exponential function has an inverse function, and it is the logarithmic function. And what that means is that if a to the y equals x, exponential function, then we can say that y equals the log base a of x. Okay, these are inverses. For whatever reason, I've always had trouble kind of conceptualizing logarithms, and I'm going to finish this series of videos without fully, getting it in hand. I have a log in my eye, I can't see, but I've always said to myself, the log is the power. So you can see that y is the power in this one. And so the answer, y, is the power. And then a is the base. That always made sense. X, then, if I ask, basically what this is saying is, what is the power that I have to raise a to in order to get x? That's what this is basically saying. And these are inverse functions. In fact, I've got a nice little shank drawing here where I've poorly drawn, of course. Y equals a to the x is the exponential function, goes through 0, 1. No matter what the base is, it's going to go through 0, 1. The inverse then is the mirror of it, and this is the log base a of x if a is greater than 1. See a previous video for what it is if it's in between 0 and 1. But anyway, this is going to always go through, no matter what the base is, or whatever x is, it's going to go through 1, 0. Why? Because the log is the power. So what is the power of 0? What is the power of 0? Anything raised to the power of 0 is going to be 1, right? And so 1 is x in every case, no matter what the base is. So everything's going to go through this one. Okay, so these are then inverse functions. And let us also now say that the natural logarithm of x, now I'm doing the asterisk part of that chapter. He does it twice. He does it first from a kind of intuitive pre-calculate, and then he does it again from a more rigorous mathematician perspective. And so we've actually, in this asterisk series, have already talked about the natural logarithm of x, but we can now say that the natural logarithm of x is, in fact, the logarithm base e of x. Okay, who knew? Okay, actually you did know, didn't you? Change of base formula. This is important because sometimes log base a of x can be complicated. And so, like, what if a is base 1.75 or something silly like that? So knowing that the logarithm base a of x equals the natural logarithm of x over the natural logarithm of a, this is how calculators calculate these things, by the way. And it can make things simpler for you too. You might be on a deserted island and not have a calculator. So knowing the change of base formula, go ahead and carve it into a palm tree so you don't forget it there. But this is a change of base formula to keep in mind. Here's the proof of it. So let's say that y equals the logarithm base a of x, right? No surprises there. If that's the case, then we know that a to the y equals x, right? Because these are inverse functions. That's true. So let's take this a to the y equals x, and let's take the natural logarithm of both sides. So the natural logarithm of a to the y is going to be y. The y pops right out there of the natural logarithm of a. And then the natural logarithm of x is, surprisingly, the natural logarithm of x. Okay, so then we can divide both sides by the natural logarithm of a. And so we have y equals the natural logarithm of x divided by the natural logarithm of y. Okay, that sounds perfectly wonderful there, doesn't it? Now, we've already said that y equals the log based a of x, right? So we now know that the natural logarithm of x over the natural logarithm of a equals logarithm base a of x, which is what we sought out to prove. Quoterat demonstrandum, it is proved. All right, change of base formula. One last thing in this video as we reach the end of the world. So what is the derivative of the log based a of x? Why, it's 1 over x times the natural logarithm of a. Natural logarithms are really handy dandy. They make everything simple. Simpler. Okay, so this is the derivative. And so let's go ahead and prove it. So the derivative of this, well, we just said from the change of base formula that this is equal to natural logarithm of x over the natural logarithm of a, right? Well, the natural logarithm of a is a constant, so it pops out as 1 over the natural logarithm of a. And what is the derivative of the natural logarithm of x? See a previous video where we find out that the natural logarithm of x is 1 over x. And so we know, therefore, that the derivative of the natural logarithm based a of x equals this. And we could figure out using the fundamental theorem of calculus then what the integral of it would be as well. But I don't think I put that in this video because it wasn't in the chapter. So I'm going to have to hold off for now. But this has been the general logarithmic function.